Today we're going to develop the Work-Energy Theorem, and we're going to talk about energy. What is energy? And these are big ideas we're dealing with today, very important ideas. We're going to talk about how energy can be stored, how energy can be transferred, and then we'll talk about the work, and we'll define this stuff called kinetic energy. And so let's begin. First of all, what is energy? Well, I have here an example of stored up energy. Okay, here they are. Can you see them? Okay, these are, that's kind of interesting looking. These are blood orange. This is a blood orange from my orange tree. And for the last year, my little blood orange tree has been absorbing photons from the sun and storing the energy that's contained in those photons in molecules of sugar, basically, fructose, different kinds of sugar. Now, what I'm going to do is I'm going to take this wedge of orange and I'm going to eat it right now. It's delicious. So what I'm doing, chewing it up, my saliva's mixing with it and starting to digest it already. Okay. Now it's going down in my stomach where it gets turned into this wonderful stuff that hopefully won't come back up the wrong way. Okay, and then in a few minutes it'll start, the stomach will start releasing little bits of it at a time into the small intestine, where the energy contained in this orange will be distributed throughout my body. And what does that energy allow me to do? It allows me to make changes to my environment, which I'm doing right now. I am speaking, which means my vocal cords are vibrating against the air, sending changes out into the environment, wiggling your eardrums. Okay, doing work on your eardrums. And so I'm able to make change to my environment. I'm able to move around, push things, lift things. I'm able to keep my body temperature at 98.6 degrees Fahrenheit, even though the temperature in the room is 72 degrees Fahrenheit. Now, if I ran out of energy, and it would take several weeks to actually starve to death, okay? Because we all have this stuff on our bodies, stored up energy. It's called fat, but it's important. It stores up energy, and if there is a lack of food, we will be able to survive quite a long time. Of course, our metabolism will slow down, and we will use the rate at which we use the energy stored in our bodies will dramatically slow. Okay, that's called power, the rate at which we use our energy. So we'll become less powerful, right? When you're tired, when you haven't eaten for a long time, and you feel very lethargic, very tired because you haven't eaten, that's your body slowing down, saying, hey, we haven't eaten for a long time. Maybe we're going into a famine. Slow down. Let's start rationing how much the rate at which we use energy. Okay, so if you're going to make changes to your environment, you need to have energy. Now, energy can be stored in various ways, and the way we store energy. We can store energy in molecules. That's called chemical potential energy. And that's what I was doing with the orange. There's energy, quite often energy that's stored is called potential energy. Gasoline in a car. That's energy, the capacity to make changes in the environment stored up in the way the molecules are arranged. Same thing is true with food or fat or whatever. I can store energy in gravity fields. gravitational potential energy, which we're going to deal with later. Okay, that's energy. Okay, if I were to hold a bowling ball, a meter over your head, can I affect change on your head using that bowling ball? Yeah, if I release it, you can fracture somebody's skull and I could lose my job, okay? But in any case, I can make changes to my environment because I've lifted something up in a gravity field. That's called gravitational potential energy. Energy can be stored in a moving object. That's called kinetic energy. Objects that have mass and are moving have the capacity to make changes in their environment. If you don't believe me, go play on the freeway, okay, during traffic, and you will find that the cars approaching you have a lot of mass and they're moving very fast, and they can make very radical changes in your life, okay, if you run out in front of them. Okay, I actually found this out the hard way. When I was the summer before my junior year in high school, I actually was a pedestrian crossing the street, and I got hit by a car. And I found out that that car actually transferred energy into me. It had energy stored up in its mass and motion. We'll talk about that later on. Now, energy can also be there are various ways of storing energy, and we're going to talk about more than just these three, but these are the three major ones. We can also store energy in, we can transfer energy. For example, when you let's say you want to make some tea. So you have some tap water, you put it in a kettle, and you put it on the burner of your stove, and you heat it up. Now, what are you doing? You're transferring energy from the burner on your stove into the water. And that transfer of what we call thermal energy is called heating. Heating is a way of transferring energy from one system into another system. And we're going to study that later. We're going to, next chapter 12 is thermodynamics. We're going to study that. Another way of transferring energy is using photons, or electromagnetic radiation of some kind. If you've ever been camping and you get really cold and you light a fire and you hold your hands up to the fire and you can feel your hand, the heat, right? You can feel that's actually radiation. That's thermal radiation into your hand. Or you're looking at me right now because light is reflecting off of my face, and so that's light is a form of energy being transferred from one system into another system, electromagnetic radiation. And we'll study a little bit of light later on as well. But what we're going to do today is talk about working, or just sometimes we just call it work. Working. Now, this is the process of transferring energy from one system into another using a force. So it's the working, or work, is the transfer of energy using force. And this is the most common thing you're going to see in everyday life. Well, actually, all of these are very common, but this is the one we're going to talk about today. Okay, so let's introduce this by example. Okay, so let's say that here's a flat horizontal surface. Let's say there's no friction here. I have a crate right here. Let's put it on wheels. Means there's no friction. It has a certain mass. And I'm going to push on it with a net force like this. Okay, now let's say this is this is a net force. Yeah, I've got gravity and a normal force, but they kind of cancel each other out. We'll talk more about them in a minute. And what I'm going to do is I'm going to move this thing through some displacement, delta x. Okay. Now, what's happening here is this. Somebody has to apply this force. Maybe this is just me standing here pushing on this cart. And when I do that, I transfer energy from my body, you know, from these bad boys right here, into the motion of this object. I do work on it. And I transfer that energy into the motion of this object by pushing on it. Okay? Now, the way we calculate what the work is, and you'll see why this is here in a minute, is we say, well, the work done, and by the way, here's the Science 1, the freshman science definition of work. We're going to go all the way through the AP Physics definition here, even if you're not in calculus. Well, you take, how big is this force? And you multiply that by how far the thing moved, delta x. And this is our most primitive, our simplest definition of work. Now, let's take a look at units here. What is force measured in? Well, newtons, but yeah, it's kilogram meters per second squared. But we'll just call it newtons. And what's a displacement measured in? Meter, it's meters. So newtons times meters gives us a unit for work. And we call them joules. And we abbreviate it with the letter J. Okay. So a joule is a newton times a meter by definition. And, well, a newton is a kilogram meter per second squared. And when I multiply that, this is a newton times a meter, you get meter squared. So a joule is a kilogram meter squared per second squared. Those are the fundamental units. Now think of this, here's why this is actually doing work. Because it's transferring energy from the person pushing on it into the motion of this object. It's going to gain energy, and what we're going to do right now is figure out how we relate this push and this displacement to how fast this thing is actually moving. Let's say maybe it starts off with some initial velocity and it's going to end with some final velocity at delta x. There's no friction here. This is the net force. So what I'm going to do is I'm going to say, hey, let's multiply. How much work. I've defined this to be work. This is the net force times delta x equals, well, here's the thing. What is the net force equal to? What's the most important equation in all of physics? The net force is equal to mass times acceleration. Now we have to multiply by delta x. Well, now this is a derivation, so, you know, somebody a long time ago thought of this. This force is constant. Let's keep the force constant. That means the acceleration is constant. That means I can use the kinematic equations. That means that I can express delta x and acceleration, and well, I'm just going to use the fourth kinematic equation. Okay? Everybody agree that if this is a constant force, I have a constant acceleration, and therefore this equation applies to this problem. Now let's solve it for delta x. Let's do the algebra. I'm going to solve for delta x. Well, I got to subtract this from v squared. So it's v squared minus v naught squared, and then I have to divide by 2a. And this will, I've now solved this equation for delta x. Well, now I'm going to substitute that expression in there, and I'm going to get
v squared minus v naught squared over 2a. So this is my net force times my displacement expressed in terms of velocity and acceleration. And what cancels out? Acceleration. And now I've got, okay, the net force times my displacement is equal to, well, let's distribute the mass in here. It's mv squared minus mv squared, and then we're going to divide by 2. So I'm going to split all that up, and I'm going to say this is 1/2 mv squared minus 1/2 m v naught squared. Now, this is an expression right here, 1/2 mv squared, that is very, very special. This was the result, well, this difference here is the result of doing work. It's also how much work this massive moving massive object can do, because it has mass and it's moving. We have a name for this. It's called kinetic energy. And we use the letter K to represent it. Now let's take a look at the units here for this expression. M, what does M stand for? Which is measured in? Mass is measured in kilograms. Okay, try again. Now, what is velocity measured in? It's measured in meters per second, so we're squaring it. So that's meter squared per second squared. What's a kilogram meter squared per second squared? It's a joule. So it is, this kinetic energy is units of joules, just like the work over here. And this gives us a very special equation. We call it the Work-Energy Theorem. And it says, hey, this is the work done by the net force. So I'm going to call this W net. Now this really means the work done by the net force is equal to, well, this is the kinetic energy the object had at the end, over here. So this was K final, minus how much kinetic energy it started with. Well, that's K initial. What is K final minus K initial? Anytime you have a final minus an initial, you have a change. Now this this little expression right here is really, really profound. It's called the Work-Energy Theorem. And what it says is that, hey, if the net force is doing work, the result of doing work is a change in the kinetic energy of the object. So we've defined what kinetic energy is. We're changing the kinetic energy if we're doing work on it. And we can use this concept to solve, lots and lots of problems. And notice that this is very much related to all the stuff we've been doing all year. It's just a different way of looking at it. And what we're going to see later on is that for some problems, you want to use the procedure that we talked about before, where you draw a free body diagram and you find the acceleration and you use kinematics, okay? For some problems, in the last unit, we found that it's more convenient to use impulse and momentum, okay? Now we're going to have another technique for looking at problems where we're going to use concepts of work and kinetic energy, and eventually gravitational potential energy, or elastic potential energy, things like that. So, and we'll get to that in a little bit. So, but this is the work-energy theorem, and it is certainly at your service to use.